Okay, let's unpack this. For decades, whenever we talk about computing, the entire conversation always comes back to one thing.
Silicon.
Silicon.
Mm.
CMOS, the technology that basically built the entire information age. But we all know the story. That dominance, which was really built on Moore's law, is, well, it's hitting a wall.
A hard wall. Yeah, it's hitting fundamental physical barriers, especially when you talk about power consumption and the heat.
So much heat.
Exactly.
Yeah.
And just the raw speed you can move signals around.
So we're really entering what a lot of researchers are calling the post-CMOS era, a time where just making silicon a little bit better isn't, it's not enough anymore.
It's not. High-performance computing needs a radical shift if we're going to keep up with the demands of AI or quantum control or just these hyperscale data centers.
And that's what this deep dive is all about. We are zeroing in on what a lot of experts think is the most promising and maybe the most transformative candidate for that future.
The superconductor electronics,
Or
SCE?
Right. So our mission today is pretty specialized, but it's essential if you want to understand the future architecture of, well, of everything. We're dissecting a stack of sources, all related to advancing SCE.
And specifically, we're leveraging the work and the roadmap that was laid out in a recent expedition seminar by Dr. Sasan Razmkhah and his team at the USC Sport Lab.
Yeah, the source material is, it's highly technical, but it's also this incredibly focused blueprint for what comes next.
Well, our goal here is to really analyze that technological transformation that's needed to get us from the astonishing potential of SCE
Unreal world.
to the practical, scalable reality of building an actual computer system, what they call superconductor, very large-scale integration, or sVLSI.
We have to move past the if and really get into the how.
Exactly.
The insights we're pulling from these sources, they detail everything. The breakthroughs in device physics, the specific new materials, and all the really complex architectural problems that have to be solved together.
All to move this technology from a lab bench into the next generation of data centers. And the promise is, it's systems defined by ultra-low energy use and ultra-high processing speeds.
It's not a small step. It's a quantum leap.
It really is.
So let's start with the sheer scale of this idea. When we talk about a post-CMOS technology, we really need to get why the old one is struggling. The sources pretty clearly establish SCE as the leading contender. So what is the fundamental, the irresistible wow factor here?
What makes it worth it?
Yeah, what makes researchers invest billions in tech that you have to cool down to near absolute zero?
It just boils down to physics. It's about energy efficiency and it's about speed. SCE is positioned as this transformative post-CMOS technology because it attacks the two sort of existential problems of modern computing head-on.
Okay.
The bottleneck we have right now with silicon, it's not really processing power. It's the huge amount of power you need to just get rid of the heat that the processing generates.
Right. Every single time one of those billions of transistors switches, a little bit of energy just becomes waste heat.
A tiny bit. But when you have billions of them switching billions of times per second,
that waste heat becomes this giant operational problem and an environmental one.
Precisely. So let's look at the energy side first. The core benefit that the source material highlights is ultra-low energy consumption.
And they give a specific number, right?
They do. It's defined as sub-attajoule per switching. And that metric right there, that's what defines this entire transformation.
Sub-attajoule. That sounds like a number from a physics textbook, not a practical engineering goal. Can you grand that for us?
It's hard to wrap your head around, yeah. An attajoule is 10 to the minus 18 joules.
Okay, so incredibly small.
Vanishingly small. To put it in context, let's look at today's tech. High performance, really low power CMOS is pushing to get into the femtojoule range.
And that's 10 to the minus 15.
Right. And your typical desktop or server chip,
yeah,
it might be in the picojoule range,
yeah.
10 to the minus 12. So moving from femtojoules to sub-attajoules is a reduction in energy per operation by a factor of, what, 1,000? Maybe 10,000?
That's insane. It's a completely different class of device.
It really is.
So why does that scale matter so much when we're talking about something like a huge cloud data center?
Mm-hmm.
If the energy is that low, you're still forced to operate in this cryogenic environment, which itself costs power to maintain, right?
That's the key question. But the energy reduction is so massive, it's exponential, and that completely changes the economics of cooling. In a normal data center, something like 40%, maybe more, of the total electric bill isn't for the processors.
It's for the air conditioning.
It's for the giant HVAC systems that are just pulling heat out of the building. The bottleneck is fundamentally thermal. So if you can reduce the waste heat from the computing itself by a factor of 1,000, you dramatically simplify all that cooling infrastructure.
So even though the chip itself needs to be super cold,
Right? Even though the SCE chip needs cryogenics, the total energy footprint of the whole system, the processor plus its cooling, can be vastly smaller than a conventional chip. And that's because the chip itself is generating almost no waste heat.
so the goal isn't just a faster chip. It's about breaking that thermal feedback loop that stops us from packing processors closer and closer together.
That's it. Ultra-low energy is really about breaking the heat barrier so that we can keep scaling our data infrastructure.
And the reason it can do that is because of how it switches.
Exactly. It's a completely different mechanism. CMOS moves charge, electrons, through a resistive material. SCE uses something called a Josephson junction to switch based on moving these tiny, discrete packets of magnetic flux.
Single flux quanta, SFQ.
SFQ, right? Yeah. And because these SFQ signals are traveling through superconducting materials that have literally zero electrical resistance, the switching process itself is, well, dissipationless. And that's where you get that sub-added joule efficiency.
Okay, so that handles the efficiency problem. But the other big draw, according to the sources, is speed. Ultra-high processing speeds, specifically tens of gigahertz. A modern CPU is already running at, 5 gigahertz? So why is tens of gigahertz a game changer for SCE, but it's not really for silicon?
This gets into something called the copper bottleneck, or more formally, the RC delay.
Right, resistance and capacitance.
Right. Even if a CMOS transistor could somehow switch in a picosecond, that signal then has to travel across the chip on these tiny copper wires. And those wires have resistance, the R, and capacitance, the C.
And that combination creates a delay, a lag. The signal gets weaker.
Precisely. And as you shrink the wires and make the chips bigger, that delay becomes the thing that limits your clock speed. It's not the transistor anymore. It's the interconnect.
So our silicon chips are basically limited by how fast an instruction can get from, say, the processor core to the memory cache.
Or just from one logic gate to the very next one. In SCE, because the interconnects have near zero resistance, that delay from the transmission lines, it essentially vanishes. The magnetic flux pulses travel at a speed that's pretty much only limited by the speed of light in that material, with no resistive power loss. So this lets you push the system clock frequency into that tens of gigahertz range, 10, 20, even higher, without the latency problems that bottleneck silicon.
So it seems like the energy efficiency and the speed are really two sides of the exact same superconducting coin.
They are.
Zero resistance gives you zero heat, and it gives you maximum signal speed.
That's the fundamental insight. And this actually brings us to the third key benefit mentioned in the sources. Cryogenic environment compatibility.
Okay.
Which, on the surface, the need for deep cooling, we're talking 4 Kelvin, so near absolute zero. That might sound like a total engineering nightmare.
Sounds like a deal breaker.
But in today's high-tech world, it's actually becoming a feature.
How is the cold a feature and not a bug?
Because of the massive, massive investment that's happening right now in quantum computing. Most of the leading quantum technologies, especially the ones based on superconducting qubits, like what IBM and Google are doing.
They already have to operate at even colder temperatures.
Exactly. They're in dilution refrigerators at millikelvin temperature. So if you're already building this huge, incredibly complex refrigeration unit anyway,
you might as well stick the classical processor that controls it right inside with it.
Absolutely. SCE technology, operating at 4 Kelvin, is perfectly compatible with that environment. It means you can integrate the classical processor, the one that controls the quantum operations, does the error correction, handles all the I/O. You can put it right next to the quantum chip.
In the same cooling system.
In the same system.
Right.
And that makes the interface between the quantum world and the classical world ultra-fast and ultra-low power. You just can't run room temperature signals down miles of wire into a dilution fridge to control quantum gates that operate in picoseconds. It doesn't work.
So SCE provides that critical high-speed cryogenic control layer.
It does. And that connection is so important. SCE isn't just a competitor to CMOS. It's also positioned to be the essential supporting actor for this whole field of superconducting quantum computing.
It creates this like a symbiotic relationship that kind of justifies the need for this extreme environment in the first place.
Well said.
So we've established this incredible transformative promise, massive efficiency, tens of gigahertz speeds, quantum compatibility. But that just begs the question.
Right.
If this tech is so clearly superior on paper, why are we just now having this conversation? Why isn't my laptop running on a superconducting processor? Here's what gets really interesting.
Yeah, this is where we move from the potential to the practical hurdles that have historically just slammed the door on mass adoption.
This is the challenge of superconductor very large-scale integration, sVLSI.
The challenge is enormous. I mean, it's one thing to build a few hundred working Josephson junctions in a lab.
It's another thing entirely to build billions of them that all work perfectly together on a big chip.
And the source material, it points to two primary sort of interlocked obstacles that have to be overcome to get to that true VLSI scale.
And these are the problems that have basically stopped Moore's law from applying to superconductors until now.
Exactly. The first is integration density. The second is manufacturability.
Let's start with density.
Okay, density. The reason CMOS scaled so well for so long is that the transistor itself just kept shrinking. For traditional SCE, the core switching element, the Josephson junction or JJ, is often pretty small itself. But
There's a but.
there's a big but. It required these bulky external passive components to work reliably, things like inductors and shunt resistors.
And why are those parts needed, and why do they take up so much space?
Well, a standard JJ needs an external resistor called a shunt to sort of dampen its switching response and make sure it resets quickly.
So that it doesn't just oscillate out of control.
Right, so you can clock it reliably at high speeds. And it also often needs an external inductor to store the magnetic energy that actually represents the signal, that flux quantum.
And these passive parts, the metal coils for the inductors and the resistive lines for the shunts, they're just huge compared to the junction.
Exponentially bigger. They might be 10, maybe 50 times the size of the junction itself.
So the part that does the actual work is microscopic, but the infrastructure needed to control it is massive. It's like having a tiny engine that needs a basketball court-sized radiator just to run for a second.
That's a great analogy, and that fundamentally limits how close you can pack your logic gates, which keeps your density way down.
Okay, so that's the density problem. What about manufacturability?
That just compounds the issue. Building these circuits means depositing these ultra-thin films of special metals and insulators, materials like niobium or specific nitrides, with atomic-level precision.
And any little mistake is a big problem.
Any defect, any irregularity, even a tiny variation in the thickness of that insulating barrier between the superconducting layers, it can just destroy the junction's quantum properties.
Yeah.
The device fails.
And scaling that process up, that high-precision, low-defect process, to the point where you need billions of junctions to work reliably across a whole wafer.
It's a monumental material science and engineering challenge, a truly monumental one.
And beyond just the physical size and making them perfectly, the sources also highlight that the physics of this SFQ logic imposes these unique architectural demands.
Yeah, things that are completely foreign to your average silicon designer.
So we can't just take a blueprint for a CMOS microprocessor and, map it onto these SCE devices.
No, and that's a crucial point, especially for, say, undergrad or grad students getting into this field. SFQ logic relies on these ultra-short picosecond pulses of magnetic flux. And because these pulses are so brief, they basically travel to the next stage in the circuit almost instantly.
And that requires a very specific structure.
It does. It necessitates what's called a deeply pipelined architecture.
Okay, so why is deep pipelining breaking a calculation into many, many tiny sequential steps? Why is that mandatory for SFQ?
Well, pipelining is a classic trick to maximize throughput. Think of an assembly line.
Right.
If a car takes 100 hours to build, you don't wait for one to finish before starting the next one. You break it into 100 stages, and a new car rolls off the line every hour. In SFQ logic, the pulse is so fast that if you didn't have a new operation queued up immediately behind it, you'd just be wasting enormous amounts of time.
So you need these deep pipelines, often requiring tens of single-cell pipeline stages for even simple math, just to keep the assembly line full and running at that tens of gigahertz clock speed.
Exactly. You have to do it to match the throughput to the clock speed.
But that sounds like a massive headache for the designers. I mean, if a simple addition needs, say, 30 tiny sequential steps instead of 3, you're exponentially increasing the risk of timing errors or things getting out of sync.
The complexity is staggering.
Yeah.
The circuit designer has to meticulously make sure that the data flows perfectly through all those stages, with perfect timing synchronization across the whole chip. It's a huge overhead.
And it requires a completely different way of thinking about high-level design compared to the flatter, wider architectures you see in a lot of modern CMOS.
A completely different mindset. And if that wasn't hard enough, there's another constraint:
Of course there is.
the low fan-out drive capability.
Let's break that down. What does fan-out mean, and why is a low fan-out such a killer for designing an architecture?
Fan-out is pretty simple. It's just the number of logic gates that the output of a single gate can reliably feed into. In silicon, CMOS gates have a high fan-out. One output can drive many inputs.
Which makes it easy to send a signal to lots of places at once.
Right. It simplifies routing key signals, distributing clock signals, feeding data to multiple places. It's just efficient branching.
But with SCE, because of the physics of these flux pulses, the gates have a very low fan-out, sometimes just one or two.
And that's the major architectural bottleneck. If you need a signal, say, an important control signal to go to 10 different places on the chip, you can't just flip the wire.
What do you have to do?
You have to insert these specialized, power-consuming, space-hogging repeater circuits, or buffer trees, at every single branch point. This low fan-out forces designers to use way more components just for routing and signal distribution than they ever would on a CMOS chip.
So the low fan-out directly works against the goal of high density.
Exactly.
Every complex function, like a big math unit that needs a lot of internal connections, it's forced to become physically much larger and more complex because it needs this whole army of intermediate buffers just to move the signals around inside itself.
Exactly right. And this is why the sources conclude, pretty definitively, that these architectural constraints demand new solutions in architecture, circuit design, and device development.
You have to innovate the fundamental building blocks themselves to get rid of those constraints.
Or you will never, ever achieve scalable sVLSI.
That sets the stage perfectly for the actual breakthroughs. If the core problem is that traditional Josephson junctions are too big because of those external resistors and inductors, how do the researchers solve that? How do they make the junction self-sufficient?
This is where we get into the cool material science and device physics. The solution is all about engineering the junction material itself to get rid of the need for those bulky external parts.
Okay.
And the sources we looked at highlight two key innovations here: the π-Josephson junction, or π-JJ, and the stacked zero-Josephson junction, or zero-JJ.
Let's focus on the π-JJ first. The sources say these junctions significantly increase logic density. So how do they do that?
Okay, so a traditional Josephson junction is called a zero-JJ. That's because the phase difference across the junction is zero when there's no current flowing. A π-JJ, on the other hand, uses these very carefully selected magnetic barrier materials inside the junction itself.
So they're building something into the material.
They are. They're engineering the material to fundamentally change the current phase relationship, and it introduces a 180-degree phase shift. That's the pi, even when there's no current.
And that 180-degree phase shift is the magic trick. But what does it actually do for the circuit?
Well, lets the junction do two things at once. It can switch, and it can self-dampen. Think of a standard JJ like a really delicate spring. When you trigger it, it needs an external shock absorber, that's the shunt resistor and inductor, to stop it from bouncing all over the place and make sure it settles back to zero quickly.
The π-JJ is like a self-dampening spring.
That's it. The inherent magnetic structure and that built-in phase shift, they provide the necessary damping internally. So there's no need for the external shock absorber.
By engineering the junction to have this intrinsic phase difference, they just eliminate the need for the bulky external components.
Precisely. This mechanism means the π-JJ achieves its purpose by eliminating the need for those bulky inductors and external shunt resistors in a lot of circuit designs. And that instantly frees up huge amounts of space on the chip.
Which leads to a massive leap in logic
A
density.
huge leap. And there's a secondary benefit, too. The sources mentioned they also do this while reducing bias currents.
So they're more efficient, too.
Yes. The specialized nature of the π-JJ, especially when it's used in certain logic families, makes them more efficient at managing these flux quantas. They just need less overall DC current to keep the system powered up.
And the source material points to a specific material they're using for this.
It does, a MnN4-based π-JJ. And that specific material choice is important because it proves that researchers have found these robust, manufacturable material stacks that can reliably generate this phase shift.
Okay, so the π-JJ solves the problem of the horizontal footprint. What about the second innovation, the stacked zero-Josephson junction? This sounds like it's a vertical solution.
That's exactly right. The Stack zero-JJ is all about using 3D integration to push the density even further. I mean, we're running out of 2D space in chip design. The Stack zero-JJ literally stacks multiple layers of active Josephson junctions on top of each other, separated by these ultra-thin insulating barriers.
So you can put 3 or 4 functional switches in the same physical space that used to hold just one. You're building a skyscraper instead of a ranch house.
Exactly. And this allows for incredibly tight, complex routing and integration of your circuits. If you want to hit that goal of 50 million junctions per square centimeter, you absolutely have to use the vertical dimension. And the Stack zero-JJ gives you a reliable way to do that.
It must be an incredible engineering feat to manufacture those perfectly aligned, multi-layer junctions.
It is. And the sources mentioned the specific material platform for this one, too. NBTIN-based stacked zero-JJs.
Niobium titanium nitride. Why that material?
Well, NBTIN is often favored in advanced superconductor electronics because it has a slightly higher critical temperature than pure niobium.
So the temperature below which it becomes superconducting is a little bit warmer.
A little bit. We're still talking deep cryogenics, but operating even a degree or two warmer can significantly simplify the requirements of the cooling system and reduce the operational costs. So that choice shows that the researchers aren't just thinking about density. They're thinking about practicality and system integration.
So it's this combination, the π-JJ getting rid of the bulky passive parts, and the stacked zero-JJ using vertical space. That's the 1-2 punch that really unlocks sVLSI density.
That's the pivotal takeaway. The source confirms that functional stacked zero and π-JJs have already been successfully demonstrated. The foundational device physics problems have been solved.
So the bottleneck now shifts. It's no longer about the device. It's about how we design and build systems using these new, better components.
Exact.
So now that the research has delivered these sophisticated, miniaturized components, the self-dampening π-JJ and the 3D stacked zero-JJ, the next crucial step is turning them into a standard set of reusable building blocks.
Like a Lego set for engineers.
Right. We need a standard logic family that system engineers can use to design everything from a simple register to a massive neural network accelerator.
And this step is really about defining the language of this new architecture. The solution presented in the sources is the development of a specific high-density logic family built on these new zero and π-JJs. They call it the high-density, high-speed phase logic family, or FPL.
Phase logic. Does that name connect back to that inherent phase shift in the π-JJ?
It does, absolutely. Phase logic refers to a design philosophy where the information, the ones and zeros, and the switching behavior all explicitly leverage and manipulate that phase difference, the pi, or the zero, across the Josephson junctions.
So it's a design method that's tailor-made for the advantages that the π-JJ gives you.
It is. It allows for extremely dense, robust, and very high-speed operation.
And the number they quote here for density is it's staggering. The FPL family achieves an impressive density of over 50 million junctions per C-meter.
That number, it really represents a watershed moment for this whole field. Older superconducting logic families, like RSFQ, they often struggled to break even 1 million junctions per square centimeter.
And that was because of the bulk of those external components we talked about.
Right, so hitting 50 million junctions per square centimeter is a massive leap forward. It makes complex, full-scale processing possible. And while, it might not match the raw transistor count of a leading-edge silicon chip yet,
It's a different game.
it's a completely different context. Each of those 50 million junctions is switching at tens of gigahertz and consuming 1,000 times less energy than its CMOS equivalent.
Which means we can finally start building these specialized, large-scale accelerators for AI or cryptography on a single chip and really take advantage of that zero-resistance speed.
Absolutely. But moving beyond just the logic gates, the researchers have to tackle the whole system-level design. And the source material really emphasizes chip designs and multi-temperature integration.
This is the reality check.
This is the reality check, getting the cold chip to talk to the warm world.
It's an incredibly complex engineering task because the whole system has to work across multiple temperature zones. You have the SCE logic down at 4 Kelvin, but the external interfaces, the memory, the power control systems, those are often at room temperature.
Or at least at intermediate cooling stages. And it's one of the hardest practical challenges there is. The chip designs they're developing are inherently heterogeneous. They combine traditional CMOS technology.
So standard silicon.
Standard silicon used for room temperature control, clock generation, and all the external data communication. They combine that with the ultra-fast SEE single-flux quantum or SFQ logic.
This CMOS and SCE integration must require some incredibly sophisticated interfaces.
It does. They're called multi-chip modules, or MCMs, and they have to be meticulously designed to manage that thermal gradient and also the electrical conversion from high-voltage CMOS signals to these tiny, ultra-low voltage SFQ pulses.
And to make it even more complicated, the sources mention they're integrating both DC and AC forms of SFQ logic in the same system. What does that tell us? Why use both direct current and alternating current?
It tells us the level of optimization they're working at. It's a sign of a really mature understanding of system needs. DC SFQ is usually the fastest form of logic. It's great for localized high-speed computation blocks.
But ACSFQ?
ACSFQ uses an alternating current power source, which is often much easier to distribute efficiently across a very large, complex chip. So it's often preferred for things like the system clock or complex memory interfaces.
So by integrating both, the architects are optimizing the chip. They're using the fastest logic where they need speed, and the most power-efficient, easily clocked logic for wide distribution.
Exactly.
That level of optimization across materials, architecture, and temperature zones, that really is the definition of next-generation system engineering. So with these capabilities finally unlocked, where is this technology going to make its biggest immediate impact?
The list of applications is broad, which confirms how foundational this is. It includes high-speed signal processing, which is vital for things like real-time sensor data, radar, satellite communications.
Anywhere you have huge amounts of data that have to be processed instantly.
Right. It's also being applied to neural networks, specifically to accelerate the training and inference for large AI models.
And crucially, they list homomorphic encryption, which is, it's notoriously complex mathematically.
That's the application that really shows off the power of this speed and efficiency game. Homomorphic encryption is kind of the holy grail for data privacy.
It lets you do calculations on data while it's still encrypted.
Exactly. But the computational overhead in traditional silicon makes it way too slow to be practical for most cloud services. If SCE can speed up those complex operations by a factor of 100 or 1,000, it could fundamentally unlock secure cloud computing. It would make privacy-preserving data analysis economically viable.
And then, of course, quantum computing, which confirms its role as that ultra-fast classical control engine for the quantum devices that are sitting in the same cryogenic bath. The sheer breadth of these applications really underscores that SCE isn't just some niche physics experiment anymore. It's a foundational computing technology that's just waiting to happen.
I think that's the right way to see it.
So we've covered the physics, the devices, the system integration. Before we look at what's left to do, let's just take a moment to acknowledge the sheer scale of the investment that's required to make a technological leap like this.
It's huge.
The source material mentions the significant funding behind this work from major U.S. agencies: the NSF Expedition, Discover, ARL, FSDL Cold Phase, and the DOE FlexBrain projects.
Yeah, and when you see that particular group of funders, the National Science Foundation, the Army Research Lab, and the Department of Energy, it's a signal. It tells you this technology has been elevated to the level of a national strategic priority.
These aren't just small grants.
No. NSF expeditions are multi-year, multi-million-dollar investments. They're aimed at tackling really foundational high-risk research that has transformative potential.
Can we break down what the goals of those military and energy projects might be hinting at?
Sure. ARL FSDL Cold Phase with the Army Research Lab. That strongly suggests a focus on secure, high-speed signal processing, maybe high-performance embedded computing for defense applications.
SCE's ability to do that with ultra-low power would be ideal for remote sensors or rapid data analysis in places where you can't have a lot of heat.
Exactly. And DOE FlexBrain, coming from the Department of Energy, that often points to large-scale scientific computation and specialized hardware. It probably relates to the neuromorphic and Ising machine hardware that's mentioned in the research scope.
So systems that are optimized for massive optimization problems and AI that could power things like climate modeling or discovering new materials.
That's the kind of thing. So this isn't just academic research. It's really being treated as mission-critical technology for the future of U.S. competitiveness in high-performance and secure computing.
And driving this specific research is Dr. Sasan Razmkhah and his colleagues at the USC Sport Lab. The context of his expertise is really crucial here.
It is. It shows the deep, specialized knowledge that you need to even be in this field.
Let's delve into that background a bit. What does his career path tell us about the skills needed to conquer sVLSI?
Well, his history confirms that he is just deeply rooted in the practical side of building superconductor logic. His PhD, which he finished in 2018, was specifically focused on low-power, high-speed computing using rapid single-flux quantum RSFQ circuits.
And RSFQ is the precursor, the sort of foundational logic family that led to the new FPL.
Right, so he spent his entire career mastering the incredibly precise design constraints that are imposed by these flux quanta systems.
So moving from his PhD to postdoc work in France, then as a professor, and now running his own lab at USC, it's a career path that's been focused solely on solving this sVLSI challenge.
Yes, and his current research scope shows you have to be interdisciplinary. It covers the full stack, from the fundamental physics of superconductor logic and VLSI to specialized architecture like neuromorphic and IC machine hardware.
All the way to the massive engineering hurdles of cryogenic integration and multi-chip modules.
And even looking ahead to quantum electronics, he's operating at every single layer of the computing stack at the same time.
Yeah.
And his current mission statement really pulls all of this work together.
Absolutely. The focus is defined as developing scalable, energy-efficient computing systems that integrate superconductor electronics with emerging cryogenic and quantum technologies. That's it. That's the definitive roadmap for the entire field.
They're not just chasing speed, they're chasing speed, efficiency, and real-world system integration all at once. So we've seen this immense progress, the π-JJs, the stack zero-JJs, the 50 million junction density, but the roadmap isn't finished. What are the remaining circuit and architectural challenges that still have to be solved?
This is the final bottleneck. And it's maybe not what you'd expect. It's primarily in the design infrastructure.
Meaning the software.
Exactly. While we have these high-density devices now, the sources are clear that challenges remain at the circuit and architectural level. The problem is that the entire software ecosystem and the computer-aided design, the CAD tools we use today, are all optimized for CMOS.
So the tools that engineers use to actually lay out and simulate the complex circuitry on a chip?
Precisely. Current CAD tools are built to handle high fan-out, voltage-based signals, and relatively shallow pipelines. They're completely inadequate for the highly constrained world of SFQ logic. Remember that low fan-out requirement we talked about?
Yeah, where every signal split needs a special repeater.
Trying to design a complex chip where every single signal branch needs a manually placed repeater is computationally and, frankly, humanly overwhelming. You can't do it at a billion junction scale.
So having the perfect logic gate is one thing, but figuring out the optimal way to connect billions of them under all these bizarre constraints is the final hurdle. The design process itself is the bottleneck.
It is. We need new CAD tools built from the ground up that actually understand the physics of flux quanta pulses. They need automatic placement and routing algorithms that can manage limited fan-out. They can efficiently insert repeaters, and they can ensure perfect timing synchronization across those tens of single-cell pipeline stages operating at tens of gigahertz.
So without those robust automated design tools, scaling up to true VLSI is just going to be bottlenecked by the difficulty and the sheer human effort it takes to design anything.
That's it.
So what does this all mean? The final step in this whole transformative roadmap isn't necessarily a new device or a new material. It's the creation of this robust, intelligent software ecosystem and architectural maturity that makes all these amazing devices usable and reliable and actually designable by the next generation of engineers.
That's the crux of it. The device physics is largely solved. We have the functional, dense JJs. The next phase is all about conquering the engineering automation and the design methodology to turn those millions of junctions into functioning, scalable, complex processors that can power the future. So we started this deep dive with this bold premise of a post-CMOS world, a world defined by ultra-low energy, sub-attojoule switching, and speeds in the tens of gigahertz.
And we learned that the historical barriers to getting there, that lack of integration density caused by all those bulky external parts, have been, well, effectively addressed through some really innovative device engineering.
That's right. The core breakthrough really is the functional demonstration of these π-Josephson junctions and the stacked zero-Josephson junctions. And that's what allowed researchers to develop the high-density phase logic, or FPL, family.
Achieving that game-changing density of over 50 million junctions per square centimeter.
We saw that this technology is being developed by top-tier, nationally funded research, with the explicit goal of creating scalable systems that can integrate logic, memory, and control for all these high-impact applications.
From homomorphic encryption all the way to quantum control. The big picture is clear. Superconductor electronics is rapidly moving from being a specialized field of physics to being a viable, high-performance VLSI technology.
I think so.
But let's circle back to what might be the single biggest engineering headache in the near term. It's often the silent killer of great technologies. We spent some time talking about the necessity of integrating CMOS and SCE,
Right.
which means these systems have to manage these complex, delicate electrical interactions across multiple temperature zones.
The interface, the point where room temperature meets 4 Kelvin, that transition is the point of maximum stress in the whole system.
I mean, just consider the immense engineering challenge of designing that electrical pathway and the control systems that have to bridge that enormous thermal gradient. The CMOS control systems are humming along at room temperature, but their signals have to be precisely converted and attenuated and sent down these specialized, thermally isolating conduits to talk to logic operating near absolute zero.
Any heat leakage, any differential thermal expansion that causes materials to crack, or any signal conversion error right at that interface.
That's the weak link in the entire chain.
It is.
So here is a final provocative thought for you to consider. The integration of the cold, fast, efficient logic with the warm, slow, but necessary control elements, that is the true frontier of this technology. So what other highly constrained environments, maybe in deep space probes or advanced medical imaging or massive energy storage systems, are fundamentally bottlenecked not by the performance of their core tech, but by the sheer difficulty of managing that thermal and electrical interface between functional layers that are operating at vastly different temperature extremes? That mastery of the thermal interface is the unsung engineering hero that has to prevail to bring the power of the π-JJ and 50 million junctions per square centimeter out of the lab and into the working world.